Yeah. So, for example, if the object move here, and it will be here. So we have this springs is compressed, right? Compressed, and this springs is stretch, right? Stretch, stretch, stretch. Okay. So this is compressed. So we can get Fs like this. Okay, Fs like this. And this is sketches, okay? So Fs also like this, okay? Fs1, this is Fs2, right? Yeah. So we have Fs total is Fs1 plus Fs2, and you can get K1x plus K2x, okay? Minus, right? Minus, because Fs is minus Kx. Then you can get this one, right? And similarly, you can analyze this system if the object is here. Okay, if the object is here, this springs is compressed and this springs is scheduled. Okay, and the same, you can get the total force, right? Okay, so this one like damping. Okay, so we will damping system of electric machines. Okay, yeah, because after some times, okay, the object will be stabilized here, right? Stabilized here. So now we have the work uh, done by arbitrary force, okay, random force. We say random force. So if we have random force, okay, it depends on how many dimensions. For example, here we have displacement, okay, and this one is F. Okay, so we need to find projection of F into the surface, into the dx, the ds. Okay, yeah. So here this is ds and this is f. You need to figure out the projection of f into ds, and then you can get work. Okay, get work. Yeah. So we finish session 1, the concept of work. Any questions so far? Okay. Now we go to the second session, power. Power. We have two kinds of powers. We have average power and the instantaneous power. Okay. So for average power, normally we use overbar here, or we use B average. Okay, AVG. So for average power is the ratio of work. Okay, the change in work and the change in time. Okay, yeah. So if we would like to calculate instantaneous power, that means the power is the function of times. You can get the first derivative, right? Derivative of work with respect to times. Okay, yeah. So here you can distinguish between average power and instantaneous power. Okay, so now this is instantaneous powers. This is the derivative of work with respect to time, and we know work is what? F dot delta R. Okay, over delta T. Delta is equal to 0. Okay, so you get F times derivative of displacement with times. What is it? This one is velocity, right? So now we can get the formulas of instantaneous power. This is the product of F and V. Okay, F is force and V is velocity. Okay, velocity. You can get power. Powers. And of course, this one is mechanical power. Yeah, mechanical power. Right? Okay, so for mechanical power, we have B is F time v. Okay. Yes. Yeah. This is not vectors because this is a scalar number. Okay. For example, here we would like to calculate power. So power is okay. This is F. Okay, this is FG. Okay, FG is over the W. Okay, so maybe we make confusion with W. So here I say FG. Okay, FG dot V. Okay, you get power, right? Okay, and then you can get the magnitude of FG and magnitude of V, right? And cosine, okay? Because this is dot product, so you get the phase angle here. So cosine of what? 90 plus 60, you get 150, right? And the magnitude of FG is mg, magnitude of V is V, and you get cosine 150. You can get this one, okay? And finally, you get minus 1.4 kilowatt, and you get negative power. Right? Okay. Yeah. So take a break, 10 minutes, and then we go to session 3. Tiếp ha. Bạn sinh viên dễ thương không? Sau khi thầy la xong nãy lại xin lỗi thầy đúng không? Đấy, em biết phải là một cái người như vậy. Việt Nam mình quên mất 2 từ xin lỗi nữa. Không, thầy nói đúng không? Okay, so we continue. Okay, so for here we need to one more thing I would like to mention to you. Okay, here we cannot use these formulas. Why? As I mentioned before, because fs is continuous, and the function of x. Okay, fs is the continuous and the function of x, like this. This one is fs and this one is x. You get the curve here, right? You get the curve. Yeah, you get the curve here. Okay, so for this case, you get here is minus x max, right? This is 0, and then this is fs. Okay, this is a linear curve. Okay, so if we would like to calculate work, this is the areas of this triangle. Okay, and work must be k x max square over 2, right? So if fs is the continuous and the variables not constant, we cannot use this one. Okay, just one more thing. Because when I double check the final exams, we have one more questions about that, and many students make a mistake. Okay, again, we use this one if fs is constant. Otherwise, if it's the function of x, we need to use iteration. Okay, just one more thing. Okay, now okay, come back. We discuss about energies. Yeah, energies. Yeah. The first one is kinetic energies. Okay, so the measures of the ability of the particles to do work because of its motion. Okay, so if we have the motion, we have velocity, right? We have velocity. So here for case A, this is the world, right? This is the world, and the springs haven't touched this surface. Okay, yeah, but we have the velocity v is v0. Okay, here v is also v0, but now we have contact, okay, between the spring and the surface. And now if the springs is compressed, okay, velocity is less than v0, and if you get maximum compression, okay, you get velocity 0. Okay, so it depends on the velocity. You can get kinetic energy, right? This is half mv square, right? We study from high school, right? High school. Yeah, just review. Okay, yeah. So if here, no kinetic energies, okay, here maximums kinetic energies, right? Okay, yeah. So if here we have kinetic energies, okay, Ke, and this one is the cases, okay, case A, case B, case C, and KD. Okay, so for case A and case B, you get the kinetics, okay, max, Ke max, okay, right? So for case C, you get, kinetic energies gradually reduced. So you get somewhere here, right? And here, velocity is 0, so kinetic energy is 0. Okay, so here we say energy diagram. Energy diagram. Okay, so now we have many kind of diagram. We have vector diagrams, okay, or phasor diagram. We have force diagram, and now we have energy diagrams. Okay, yeah. Any questions? Như càng ngày đi học càng ít thêm đứa nhỉ? Ha, đến từng cuối kỹ quá trời nghỉ ha. Không Hạnh? Hả? Đức Hạnh, Đức rồi. Đức đi học hả? Không Phúc có đi học không? Của mình Hạnh đi học hay không có Phúc ha? Okay. Yes. Okay. Now, we need to demonstrate how can we get the kinetic energies. That is half mv square. Okay, so we can take these spring systems as an example. Okay, so we calculate the work done by the block on the spring. The block. Okay, the block on the spring. Okay, yeah. We calculate the integration from xi to xf, okay, minus fx dx, okay. What is fx? Fx is on the block by the spring, okay. It's to the left, okay, yeah. in this negative x direction. Okay, so that means here is y, and here is x. This is origins. Okay, yeah, origins. Yeah. And then when we apply Newton's second law, you can guess here, you know, fx is max, and minus fx means minus max. And ix is derivative of vx with respect to time. You get minus m dvx over dt. Okay, so now we have minus mx, and then you relate to here, right to here. Okay, yeah. Because for the spring system, sorry, I mean for this spring force, okay, is opposite direction to this moving direction. Okay, so here minus mx is minus m derivative of vx with respect to time. Okay, and then you bring to here, you can get work. Remember, this is the work done by the block on the spring. Okay, so now we just calculate the iteration. You know, we have minus m dvx dt blah blah blah. Okay, vx dt. Okay, why? Because vxe dx over dt. Okay, look here. This is dx. Okay, this is dx. So actually, we have work is I to f. Okay, yeah, minus m dvx over dt, and now you get dx, right? And dx over dt is vx. You can get I f minus m vx. Okay, dvx. If I time delta t here and I divided by delta t here, I get this one. Do you read me? So here you have minus m vx dvx over dt and dt. Okay? Yeah. Yeah. Or you just let this one. Okay. So here you get the Vx, okay? So here you can get W is IF minus M Vx dVx, okay? So here must be Vi and this is Vf. So if we have dx, this one must be xi and xf. Now we take the derivative of Vx, so you get Vi to Vf, okay? Yeah, we change the boundary. If we have dx, this is xi to xf, but now you get dVx. So now you get Vxi VXI, sorry, VI, and then here is VF. Okay, and at the beginning, VI is max, VI is V0, and when the spring stops, you get VF is 0. Okay, so finally you get here, this is kinetic energies. Okay, any questions? Yeah. Any questions? Okay, so I just demonstrate to you why we have kinetic energies is half mv square. Okay. Yeah. So if we have Vi different from 0 and Vf different from 0, you can get work is what? A half m Vf square, right? Minus half Vi square, right? Here I say Kf, and here I say Ki. So Kf means Case F means final kinetic energies, right? And case IE, initial kinetic energy. I say this one is delta K. So work now is delta K. Okay, we have the change in kinetic energies from initial position to final position. Okay, yeah, good. Okay. This is work external, right? Work external. Remember, work external. Work external means the work done by the external force. Okay. So for the system, for example, we have the spring, right? We have the spring. So we have the work done by the spring and the work done by the external force imparted on the objects. Okay. Yeah. Remember that. Here, external. Yeah, I just mentioned here. I just mentioned here. Now we have the kinetic energies, the work from external force. Okay, external force. But now we don't have sprint. We just have only one external force here, right? Yeah. And I mentioned before, if F is not constant or F is the function of, yeah, the function of time, the function of x. Okay, we need to calculate iteration. So we have external work is xi to xf. Okay, the total force. We apply Newton's second law. You get ma dx. Okay, ma dx, and ia derivative of velocity with respect to time. Okay, so now you get m dv over dx, and dx over dt is time dx. Okay, with time dx and divided by dx. Okay, the same with this one, right? Right? Yeah. Right. Yeah. So look, dx over dt is v, right? M here, dx over dt is v. Okay, dx and dx we delete, you get dv. Okay, look, if we calculate the derivative of x, you get xi to xf. But now you change, you change. Now we take the derivative of velocity. So we have vi to vl. Okay, so you can get this one. Okay, half mvf square minus half mvi square, which I just discussed here. Okay, so here we say kf, final kinetic energies. This one is ki, and here you can get delta k. Delta k. Okay, yeah. Why we need the delta k is because for lecture 6 we talk about energy conservation, and we need to consider delta k is 0 or delta k is higher than 0 or delta k is less than 0. Okay, energy conservation. Okay, yeah. Delta k is what? Delta k is the change in kinetic energies, right? Yeah, of the systems. Okay, so now we know the kinetic energies is d phi. Okay, if we see this symbol, this d phi, right? D phi by blah blah blah. So case E d phi by half m v square. Okay, yeah, yeah, this one I mentioned before. Okay, any questions so far? Yeah. Yeah, we already know what's the difference between speed and velocity. Just to review, we calculate speed is the ratio of distance over time, and this is the displacement over time. Okay, yeah, just to review. Okay, we know. Yeah, example. We would like to calculate VF. VF how many? Okay, this is initial position. This is final position. At this initial position, we have VI. Okay, VI, VI. Yeah. And this is the rest, right? This is the rest. Because this is the rest, so VI must be 0, and XI must be 0 because this is steady state, this is the rest. Okay, yeah. And after some time, with the delta X displacement, you can get VF. Okay, we can get VF. And of course, we know VF must be positive. Okay, yeah. So we have the formulas. We have external force. We have external work. We have external work because of external force. Okay, external force. So you get Kf minus Ki, and Kf is half mvf square. Ki is what? Half mvi square, right? Vi square. But Vi is 0, so we get this one is 0. You get half v mvf square. Okay, yeah. So external work is what? It's what? Look now, you see that the magnitude of force. This is constant. Okay, this is constant, so we can use F times delta R times cosine theta. Theta is the phase angle between F and delta R. Okay, so that's the reasons I come back to the reverse slide and mention to you. Okay, so F is constant, you can apply that product. Okay, yes, yeah, because of this example. Okay, so now look, we have for work E F dot delta R or delta X, okay? But you can see F and delta X, okay, are in parallel. So we have cosine of 0, you get 1, right? So F is 12 and delta R is what? 3, okay? So you get 36, okay? So now we can get VF half M VF square E 36. So you can get VF E 72 over 6, take the square root, and you get how many? Yeah, 3.5 meter per second. Okay, I read for this one. Yes. Okay. Any questions so far? So if the final exams, I give you the function of f, okay? For example, this is xi and this is xf, and we have the function of f like this, to be careful. We need to take the integration from here to here. You get this area and this area, right? So we have a1 plus a2, right? Right? Because this one, we can apply dot product, but this is linear curve. Okay, so we need to take on integration. Integration is area. So you get the work externally a1 plus a2, right? Okay, you remember that, please. Any questions so far? Khoa, any questions? Khoa bot? Khoa bot không? Any questions? I remember we have one Indian student, but he's okay. He normally is absent. Okay, so yeah, I will ask. Sorry. Oh yeah, that's okay. Bangladesh student. Okay, he's absent. So I will tell teaching. I no, I will tell Miss Lin.
It's over there.
Oh, sorry. Okay, you remember if you're absent, okay, if you're absent more than 4 classes, okay, tell the course immediately. Yeah, we need to follow the regulation. Okay, yeah, it's easy for me to remember you, okay, because you are foreign students, okay. But if some of Vietnamese students, okay, take absence, maybe I don't remember. Okay. So yeah, this example is very interesting. Yeah, you have 3 minutes. Try to understand it. So for these systems, yeah, we define a whole systems, okay, a whole system, including that portions, including these objects, right? Refrigerator, okay, and blah blah blah. Okay, I mean the whole systems, yeah. So we need to determine the work, right, done by that person, right? The work done by that person. Okay, so here we have two kinds of work because we have two forces. Okay, so the force come from the person and the force come from, yeah, the earth. I mean gravitational force, right? Right. So that means we when we calculate external work, we have the work by the man and the work by gravity, gravity, and equal to zero. Why equal to zero? Because we consider the whole system here. Because this is the whole system, so no energy change between outside, yeah, and inside system. You know, because this is the whole system, the whole system. Okay, yeah, we will study lecture 6 about energy conservation, and you can understand what is the whole system. Okay, so here this is equal to zero. Yeah, so the work by man is minus the work by the gravity. Okay, and the work by the gravity EFG, right? Is FGs. Yeah, EFGs. This is constant, right? This is constant. So we can apply FG dot delta R, delta R, okay? Delta R. So delta R means from the bottom to the top, okay? That means here is delta R, right? Right? This is XI and this one is XF, okay? So we get the coordinates like this. We get the coordinate like this. Okay, this one is y, this one is x, this is reference coordinate, right? Reference coordinate. Yeah. So we can get this is fg, you know, and this is delta x. Okay, so we have magnitude of fg is mg, and the magnitude of delta r is what? Is L, right? Is L. And the phase angle between delta R and FG. Okay, this one is 90 degree and this one is theta. This one is theta, so this one is theta, right? So you get cosine what? Cosine 90 plus theta. 90 plus theta. Okay, so cosine of 90 plus theta is sine theta, right? Sine theta. So L times sine theta, L, this is L times sine theta, you get H. Okay, so if you can, if you see here, we have the work by man mgh. Okay, so the work is irrelevant to the length, right? To the length of this ramp, this ramp. Okay, yeah. So we conclude that the work depends only the height of the ramp. Okay, so the man must do the same amount of the work. Okay, regardless of the length of the ramp, right? If we have smaller angles, okay, we also have the same work done by the person, right? Yeah, just a very common application about the work. Yeah. Okay. Questions for you. We have electric motor, right? We have electric motors. Yeah. And this is a shaft, right? So if the shaft rotate, we need what? we need force. Okay, if you would like to calculate force, we need torque. Okay, torque, right? With how F you get torque because the rotation is circular motion. So can we calculate work? Can we calculate work done by the motor? How can we calculate work? Okay, so the work here now you think about energy, right? So this motor must consumes electrical energy. So now the work is electrical energy. You need to calculate how much electrical energy is to be consumed by the motor, right? Right? Okay. So this is the ideas. We apply the theory of physics one into electric machine. Okay. Yeah. Think about it. Easy, right? Yeah. So for now, the second one, the potential energies. Potential energies. Of course, we know, right? From the high school, we know. So very quickly. So here we consider initial position here. And this is final position. Okay? And of course, the book will go upward, right? Will go upward. Yeah, this is initial position. So we have external work. So external work E F dot delta R. Okay, of course F must be constant. Please remember it's constant. Please. Okay, constant. So now we can get F if we apply Newton's second law. You get F equal to mg, right? This is external work. So external force. This is gravitational force. Okay, so they must be equal. So you get mg and delta r is yf minus yi. Okay, so you can get mg yf minus mg y. This is the high level, right? Yf and yi is high level. High level. Yeah, high level. Okay, or we can say we have UF minus UI. Normally, the symbol of potential energy is U. Okay, the UU. Okay, UF minus UI. So UF means the final potential energy of the system, and UI is the initial potential energy of the system. Okay, or we can get this one the delta U, right? Yeah. Here we can say gravitational potential energies. We can say gravitational energy. So normally here we say UGF, UGI, and this is delta UG. Okay, gravitational potential energies. That means the potential energies is produced by gravitational force. We say gravitational potential energies. Yeah, gravitational potential energies. Okay, yeah, we say we have UG. So we have the external work A delta UG. That means we have UGF minus UGI. Okay, UGI. Yeah. Yeah. Now we go to for another one, elastic potential energies. Elastic potential energy. So elastic potential energy is produced by the spring. The spring. So if we have a spring, we have elastic potential energies. Okay. So look at the equilibrium. We get reference position x is 0. Okay, x is 0. And at the final position, okay, when the springs is compressed or extended, okay, you get this is xi, so xi is d and xf is 0, okay. Yeah. And of course, we need to calculate integral because fx is a function of x. Okay. So here you can get xi is d, xf is 0, fx is minus kx dx. You get minus kx squared over 2, 0 to d. So you get half kd squared. So now we have elastic potential energy. UE is 1 over 2 kd squared. Okay, this is x. This equal to x. Okay. X, what's the x? X is compressed distance or extended distance. It depends on a compression or a sketching. Okay, stretching respective. Okay, yeah. Example, we have the system. Okay, this is equilibrium. This is equilibrium. Yeah, equilibrium. This one is easy compresses. Okay, easy compresses, and this one is already compresses, right? Already compresses, right? Or we say it's max compress. You get X max, right? Do you read me? Yeah. So at the beginning, of course, external, we have external force. Okay, we have external force, but external force imparted on the objects, okay, that haven't contact to the spring. Okay, so no energies, no energies from the spring. Okay, 0, 0, 0. This is kinetic energy, potential energy, the potential energy, right? Now for here, of course, this one is F external, and this one is Fs, right? F external come from the hand, right? And Fs, yeah, come from the spring. Okay, they are. So if the magnitude of external force higher than Fs, okay, continue to be compressed, okay. So here we have potential energies. Okay, actually here we say elastic potential energies because now we have X. Okay, and of course we know U is a half K D square. Okay, now this is X. Okay, and here you get maximum compression. So now we have UAA half K D square, but now D is what? X max. Okay, so you get maximum elastic potential energy. Okay, and you get maximum total energy. Okay, so this one is physical model, this one is energy diagram of a system. Any questions so far? So is this questions and questions? Cái chọc hạnh mà mốt nghỉ giận thì bọn nghỉ học. Mốt em không thèm nghịch điện nữa, chỉ qua em nghịch tiền đó qua học kinh tế. Mấy năm nay thầy dạy ở đây gần 10 năm, thầy đang tìm một cái học trò nữ để nó làm, thầy hướng dẫn tới PhD luôn, tới tiến sĩ luôn mà chưa có bạn nào. Có một bạn theo cái lĩnh vực renewable energy hiện nay đang làm lab engineer ở bên Đức ở trường Darmstadt. Một bạn nữ duy nhất theo ngành renewable energy. Ngoài ra thì hầu như các bạn hay theo automation technologies, information communication technologies. Những khóa mới đây thì theo MSE. Bây giờ điện hiếm lắm. Tìm một em sinh viên tốt nghiệp ngành điện thuần túy, hệ thống điện lực hiếm lắm, chê là hiếm. Và hiện nay thì có 2 học trò mà đang định hướng cho nên bạn hãy theo. Dĩ nhiên ứng dụng những công nghệ mới về bán dẫn vân vân. ITA rất là giỏi, tư duy rất là tốt. Một anh thì Hai anh có hai cái tư duy khác nhau. Một anh thì tư duy về viết kỹ thuật rất là giỏi, tốt, tư duy vẽ hình, tư duy, còn một anh tư duy về phân tích, toán học, lập trình là tốt. Hai anh. Và chuẩn bị có một anh nữa rất giỏi, mặc dù học trong lớp chỉ có khoảng 2.5, 2.4 như thôi, nhưng mà tư duy nghiên cứu rất giỏi. Chuẩn bị thầy đang hướng dẫn đại học tháng 6 này tốt nghiệp, sẽ học master, rất giỏi. Gia đình tạo điều kiện xây dựng cái hệ thống năng lượng tái tạo 100 mấy chục triệu, xây dựng trăm mấy triệu. Thì thay vì sử dụng cái nguồn đó cho nhà của nó thì nó làm nghiên cứu luôn. Rất là hay. Okay, next. Yeah. We consider these ones. Okay, so now look, we guess X max. Okay, and then you release the hand. Okay, you release the hand. So when you release the hand, the object back to this equilibrium state, right? Back to the equilibrium state. And we need to analyze the energy, okay, further. So here, of course, you can get the maximum compression. So potential energy is max, total energy is max. Max means 100%. Okay. Right? Okay. So here, so when you release the hand, now the object is moving. The object is moving, so we have velocity. So if we have velocity, we think about kinetic energies, right? Kinetic energy. So that is half mv squared. Okay, so now we have kinetic energies. Of course, the total energies is 100%. So if we have, for example, here is 70% of kinetics, so we have 30% of potential energies, right? Because for the potential energy, U is half kd squared, Now, this is smaller, so U is smaller, right? This smaller. And here you can see the block, the springs, okay, is back to the equilibrium state. So D is 0, right? D is 0, so that means UE is 0. We have no potential energies. We have max kinetic energies, max total energies, right? Okay. So because we have multiple choice questions in the exam, so we need to select which cases, okay, are corresponding to the different figures here. Okay. Yeah, so we need to make a connection. I mean matching. Okay. Finish lecture 5, part 1. Now review. Okay. Sorry. Hello. Okay, so now review, and we have some multiple choice questions, okay, to give you more extra point, okay, yeah. What is it? You think about constant acceleration, okay, constant acceleration. So if we have constant acceleration, we have 5 important formula, right? Yeah, we discussed many times, okay. So if the questions give you constant, okay, give you initial velocity, and we can calculate final velocity, right? Right. If we know delta x. If we know delta x, okay. Yeah. If we know ax, we know delta x, we know vxi, you can forget. Now, questions. 5 minutes. Good. And of course, you will get some extra points if you get the correct answer. I think it's easy, right? And after that, you take the pictures and inform TA. Okay, he will update your action into extra points. Okay. Super sad. Female first. Are there any female students who haven't got any extra points? Raise your hands, please. 30 seconds for female. Anyone gets the answers? How are you? What's your name? Sorry? Bui. What's your answer? I. Is that right? Okay, now check. Okay. Of course, we need to calculate based on this formula, right? Okay, and oh, congratulations. So, full name is? $2%. Okay, congratulations. Next. Of course, we review the theory. Okay, the work is done on a system. Remember, by the external force. Okay, the external forces. Okay, I mean the forces from outside the system. Okay, so yeah, we can calculate work if we have what? We have constant force. Okay, yeah, I mentioned before. Okay, we apply dot product if we have constant force. Otherwise, if f is the function of x, the function of time, we need to use the iteration. Okay. Next, multiple choice questions. Okay, 3 minutes. Female first. Okay. So. How many female students? Yeah. Okay, now your turn. Okay. Yeah. And A B C D E F G H J K L M N O P. We have a grain. Do you know grains? That means Okay, we have grains, rollers, rudder, okay, right, into place at constant speed. Okay, constant speed. Consider the work, okay, WGs done by gravities, okay, and the work WT is done by the tensions in the cable. Okay, so now we have you know rudder is the thanh ngang dầm rồi đó, mấy cái thanh ấy là okay. Okay, so we have tension force, right? This is the grain, right? The grain. Okay, and this one is FGs. Okay, so what is true? We need to calculate and remember the moving directions in this one, right? Moving direction. Okay, so now here you can calculate the work from the tension and the work from the gravity. So the work for the gravity must be H. Sorry. Okay, now your answer please. A, B, C, D, E, F, G, H, K, L, M, N, O, P. It's B. Okay. Very easy, right? Very easy. Okay. Yeah, because we discussed about the work. Okay, and if F is in the same direction, the moving direction, you get work is positive, right? And then if you get higher than 90 degrees, you get work negative, right? Thì có 25 câu à, giải câu này chưa được phút nữa. We have 25 questions, okay, with 90 minutes. So every question you have 3 minutes, okay? So this question maybe 20 seconds to get the answer. I don't know, could be B. Okay, I don't know. Is it B? That's correct. Oh yeah, okay. Please, okay. When we finish, the class today, take the pictures and update to teaching system, okay? What else? Oh, yes, okay. Now we consider that versions, okay? So that version does positive, negative, or zero work on the box, okay? Now, mail, okay? Very easy, okay? So skip. Very easy. Very easy. Okay. No opportunities for male students. Okay. And now we review, right? Yeah. So if we remember that we need to consider displacement, displacement. And then if the velocity or force, okay, are in the same direction with the moving directions, okay, you get work is positive. Otherwise, work will be negative, okay. Work will be negative in this case, okay. Displacement here, but work here, force here, so the work will be negative, okay. Oh, questions, continue, come on. Okay. In which of the three cases, okay, does the force do negative work? Okay. Okay, now male students, okay. I will font we need a list. We need a list of students, okay? A list. Let me check. We need a list of students. We need a list of students. Okay. Lemon coin. Lemon coins, are you here? Okay. Nguyễn Kim. Oh, now your answers, please. A, B, C, D. Okay. Please answer to me. You choose D. Me too. %. Okay, remember it's minus. Continue. Continue. Bây giờ thằng Kim sẽ chỉ một cái thằng tiếp theo, chỉ bất kỳ thằng tiếp theo đi ha. Okay, so for ABCD, we have some hints here, right? Remember, draw answers. Why not? Come on, ABCD. Okay, what's your name? Trần Minh Chí. Okay, next. Okay. See, read carefully the questions. Okay, the questions ask us what is the work done on the pole. Okay, by the 10-Newton tension force in the string during one revolution. During one revolution. Okay, so now you. What's your name? One. Your answers? Okay, you don't have answers. Mine are 2%. Next. Now you. Okay. Answer. You know why, right? Yes. Because we get the theta is 90 degrees. Okay, theta 90 degrees. So cosine theta is 0. Okay, yeah. So what's your name? Ethan. Next. Now we go to kinetic energies. This is we review a little bit. Okay. So we have translational kinetic energies. Okay. Yeah, you get initial position, always say before, and final positions we have. Yeah. Um, we get the constant acceleration. Okay, constant acceleration. So we can get the work will be kf minus ki. We discussed before. External work is kf minus ki, and kf is half m vf square minus half m vi square. Okay. Yeah. We have rotational kinetic energy. We have example before, right? So for this one, we need to calculate velocities, but this one is angular, right? Angular velocities. Okay, not translational velocity. This is angular. And angular velocities is v. The v is omega r. We know before, right? R is radar, so omega angular speed. Angular speed. Angular velocities, okay? Angular velocities. So we can get the velocities. So the velocities, I mean, the instantaneous velocity is angular speed times r. So if we know v, you can get rotational. Sorry, if we know omega, we can get rotational kinetic energies, and the kinetic energy for rotational motion is half I omega square. Of course, omega is angular velocity, and I is the moment of inertia. Okay, of course we know, right? We know how to calculate the moment of inertia from high school. Yeah, we make the experiment, okay, and then we can get inertia moment. But we don't have enough time, so for this course we haven't studied how to calculate the inertia moment. But for high school we know, right? So now we have the comparisons between translational kinetic energies and rotational kinetic energies. Okay, so here we use just the normal velocity, but here we should use angular velocities. Okay, square. And here we use mass. Here we use moment. Okay, the moment of inertia. Okay, questions? Very easy. Okay, just give it very easy. Now we consider this one. With box, with box experience the rate exchange in its kinetic energies. Okay, I mean we have the box here. You know, for the box we have different weight, right? Different weight, different mass, different mass. We have different masses. Okay, we have 1 kilogram, 2 kilogram, blah blah blah. Okay, so ABCD, you need to figure out which answers having the biggest chance in is kinetic energies.
It's about
We have we have this distance, right? We have this delta R. Okay, yeah. Frictionless floor. Okay, frictionless floor. You know, so that means you get work a what half m vf square minus vi square, right? Right? Alo. Dạ, xin chào Linh. À, Vẫn bình thường, vẫn làm thí nghiệm được bình thường, không vấn đề gì. Cũng có mấy con cũng chưa có sử dụng, mấy cái bộ mấy cái con mà traveling way á thì chưa sử dụng, còn mấy gale kia thì vẫn chạy ok, vẫn test được. Ừ. Không được, cái này nó thuộc về tài sản của trường chứ không phải tài sản cá nhân, cho nên là mượn thì không được, chỉ có thuê không được, cho nên đó là quy định của trường. Ví dụ như có thể là thuê, làm một cái hợp đồng thuê sử dụng thì có được, thì được. À, nhưng mà anh cũng không biết là cái chi phí nhiêu, thì mình bên chỗ kế toán nó sẽ có cái danh mục á, danh mục gọi là, nếu bị thì nếu em cần thì để anh hỏi giùm cho, để cái mình làm cái hợp đồng mình ấy thôi. à, nhưng mà anh cũng cũng không hứa để hỏi để xem cái nào anh gửi thông tin, thì cái gì em sẽ rồi ok. à, à, ừ, à, ok, ok. 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 Đến hỏi đi, cái gì anh sẽ gửi thông tin cho. Cái kết bạn Zalo đi, rồi cái gì vậy trao đổi với Linh cho vậy. Ok, bye bye. You ready? So you can use the formulas. Work is what? Is right? We have we can use that formula. That's okay. And we need to consider the mass, right? The mass. Okay. And we also consider this magnitude of force. Magnitude of force, right?
Just calculate the force because I calculate and the mass cancels out.
Okay. Yeah. Because we have frictionless, right? Yeah, frictionless floor. Okay. So we don't have friction force, right? Right. Yeah. So the answers will be next one. You D. Okay. Yeah. D. Yeah. And of course we have explanation, right? Yeah. We have kinetic energies. Yeah. What's your name? Okay, so very easy, right? Now we just change the direction of force. So we need to calculate fx, right? Fx. This one is x-axis. This one is x-axis. Okay. And then, the answer is B. Okay, because this one will have more magnitudes of the force, and the phase angles is smaller. Okay, cosine theta is higher than cosine 45. Okay, cosine 30. So we delete this one, we don't care this one, we don't care this one, and we compare this one to this one, right? And here you get the higher magnitude, so you get higher. Okay, higher is final speed. Okay, higher final speeds. Of course, initial speed is in the rest, right? In the rest of is in the rest of the find the initial velocity is 0. Okay, is 0. So now we have delta k is half m vf square minus vi square, right? And this is 0. You get half m vf square. Okay. And how can we calculate VF? You know, VF square is V I square plus 2AX, okay, delta X, right? Delta X, okay. And VI square is 0. So here, you know, yeah, IX is constant, okay? IX is constant. Yeah, so we can calculate Vx, okay. Or here, you get the delta K, right? Delta K is, yeah. And delta K is what is F time D, okay? F time D. So if the case is higher, that means the VF is higher, right? Okay, do you read me? Yeah. Okay. So for this one easy, okay. So we finish the lecture 5, part 1. Okay. Now we go to lecture 5, part 2. Maybe it's 8-minute break. Okay. 8-minute break, and then we go to lecture 5, part 2. Okay. Dạo gần đây tỷ lệ đột quỵ ở sinh viên cao lắm ha, đừng thức khuya ha.
Thì xăm hình đấy, cái mặt xăm trong hổ là thằng chuột vậy đó.
Okay, so now we continue lecture 5, part 2. Yeah, of course we need to review some theories about rotational motion. Okay, so we have if we have circular motion, we need to consider the angular position theta. Angular position theta. Yeah. And the unit is radians or degrees. After that, we can calculate the angular velocity. This is the first derivative of theta with respect to times. Okay. So theta is radians and the time is second. So you get the units of angular velocities is radians per second. Okay. Yeah, and we know omega m is 2 by fm. You can get angular velocity. Okay. Now we have angular acceleration. We say alpha. And alpha is the first derivative of omega with respect to times. Okay. So I mentioned before, if we have circular motion, we need to calculate torque. Okay. Torque is the key point, is the key parameters of circular motion, right? So when we analyze any electric machines, we need to calculate torque always. Okay, we have load torque, we have motor torque, okay? We have induced torque, okay? So how can we calculate torque? And yeah, at the high school, we know torque is the dot product between force applied and perpendicular distance. Okay, distance. Okay, I mean force and distance. Force and distance. Or we say force ends. Force ends. Distance, this, okay, distance, d. Okay, d. For example, here this is d distance. Okay, so here we have force, right? Force, and this one is the center of this of the circle. Okay, so you get here is the distance. Here is perpendicular distance, right? Right. This is 90 degrees, so you can say F times D, right? F times D. F times D. Okay. So now we can calculate torque, right? Torque. And here we know for this phase angle is the theta. This phase angle theta. Theta is what? Theta is the phase angles between R and F, right? This one is R and this one is F, right? We just translate F here to be here. I mean the tip of F to be here. And the tail, right? The tail of F to be here and the tail bar here. So you get theta is the phase angle between R and F, theta. Okay, this is theta. This is theta, so this is 180 minus theta. Okay, and then you can get distance, right? This is the R sine 180 minus theta, you get R sine theta. Get this one. Okay, yeah. And remember that theta is the phase angle between R and F. You can calculate torque, right? So for this case, this is special case because torque is zero. Torque is zero. And if we have F here, you know, we have torque direction will follow counterclockwise. Counterclockwise. Okay? Yes. And then if F is here, you get clockwise direction. Okay? So we have two kinds of torque directions, clockwise direction and counterclockwise direction. It depends on the direction of external force. Right? Okay. So if we apply Newton's second law for straight motion, you can get F is m times a. But when we apply Newton's second law for rotational motions, you get torque is J times n. So what is J? J means inertial moment. And n is angular acceleration. Okay. So if we have circular motions, okay, we normally use torque. We don't use total force. Okay, no net force. For straight motions, we use net force. But for circular motions, okay, we normally use torque. Torque. Okay, torque. Okay. Ba đứa đó lặp lại nữa đó. Nói như chú con người. Thấy mấy mấy gốc đó, gốc nhà lá mà đó, nhìn gốc nhà giàu này nè, ngồi nó im lặng, nó biết hay nó không biết gì nó cũng ngồi im lặng tôn trọng. Với bạn này thì giảng hoài mà nó không thấm lỗ tai, mới nó gọi là đàn gãy tay gì. Nó không thấm vô được, không hiểu nổi. Khổ thế. Tụi bay thích im lặng thích hơn hay là ồn ào thích hơn, náo nhiệt thích hơn trong lớp học? Tụi bay đang học, tụi bay nghe các nói chuyện tụi bay thấy bực bội không? Mình là người học thôi, nghe đứng ở phía cạnh người học thôi, lải nhải kìa không? Mà đây là văn hóa của sinh viên Việt Nam luôn nữa, chứ không phải chỉ trường này đâu, trường khác không vậy. Chỉ khi nào mà thầy dạy những lớp thạc sĩ đó, thạc sĩ trở lên đó, thì họ mới thực sự là tử tế, tức là họ đã trải kinh nghiệm, họ đi làm rồi, họ có kinh nghiệm, họ có gia chạm rồi, họ có gia đình, có con cái, và giờ họ rất là im lặng, họ rất là lịch sự. Còn mình trẻ, thêm chữ nữa, trẻ gì, trẻ trâu, nói không thấm nổi. Về hỏi ba mẹ của thầy nói đúng không? Mà cứ lặp đi lặp lại hoài cái việc này nha. Sao tụi bay thi tụi bay chưa thi 1 chấm lặp đi lặp lại hoài. Địa ba đó chính là thi cho được 1 chấm nha. Nó thi được 0.5 nữa ghê. Okay, next. Work. Okay. So for our lectures 5 part 1, we already know how to calculate work, right? And the work is F times F dot R. Okay, F dot R. Yeah, if we have constant force, and then if force is not constant, force is random, we need to use iteration, right? Iteration. So for the rotational motions, we work is the application of the torque and through an angle. Okay. So this is the formula to calculate work for straight motions. Okay. For us, like this. So for circular motion, rotational motion, we calculate work is the iteration of torque times the theta angle. Okay. Yeah, angle. Okay. So if the torque is constant, like F, okay, you get work is torque times theta. Torque times theta. Okay. So now you know how to calculate work for rotational motion. This is the product of torque and phase angle. Okay. Yeah. Yeah. Power. For straight motions, you get power is what? Power is F dot V, right? We discussed before, okay? So for rotational motions, we calculate power is torque times omega, okay? So up to now, if we would like to calculate powers of rotational motion, that's a torque times omega. Omega is angular velocity, and omega is what? Is 2 by n divided by 60. Okay, so if they get V, you can get V is omega times R, you can get omega to V over R. It depends on the questions given. If the question given RBM, right, and RBM, you can calculate omega here. Or if we know velocity, I mean internal velocity and radius, we calculate omega, and then you get power. Okay, yeah. And of course, we know how to calculate torque. Torque is B over omega, or torque A F times D. Okay, this is perpendicular distance. Okay, yeah. Now go details. We talk about energy conservation. Here, this is very easy. I mean, it's a very simple example. We have the system like this. Okay, I say this one is systems because we have the objects. Okay, plus Earth. Okay, so if we have Earth, we have gravitational force, right? We have we need to consider gravity. And And for this one, we have G. This is gravitational acceleration. G is minus 9.8 meters per square second. Okay, so this is constant. This is constant. This is constant. So at the beginning, we are here. We are here. So you get the high level is H. Okay, and at the beginning, you know, Vi is 0. Of course, Xi is H, right? Xi is H. So Vi 0, so we have no kinetic energies, and you get potential energies, right? You have potential and potential into mgh. Okay, yeah. Or you can apply the Newton, the Newton second law and constant acceleration. Okay, to demonstrate, we get U, G, and K. Okay, so here, look. Of course, G is constant. Okay, gravitational acceleration is constant. So we can apply some important formulas of constant acceleration model. Okay, so here we have Vf square is Vi square minus 2G. Okay, Yf minus Yi, right? This is one of important formulas of constant acceleration model. Okay, Vi 0, skip it. So you get what? You get the Vf or Vy is 0 minus 2G. Okay, Yi is X, right? This is Yi, not Xi. And Yf here, you know, this is you are here, and then after some time you get you here. Okay, so here you get the high level H over 2. You get this one. Okay, so you get GH. GH. Yeah, GH. So now you get Vy square or Vf square HGS. And then we can calculate kinetic energies, okay? So kinetic energy here is what? A half m Vf square. That means you get half. Vf is what? Vf is Vf square HGS. So you get a half mgh here. Okay? And you know the total energy is mgh. Okay? So here, the total energies, E K plus UG, you know, we get energy conservation. So here, if you get gravitational potential energy is half mgh, so kinetic energy, you get the other half mgh. Okay? Yeah. Yeah. Okay. Or if you would like to calculate UG, that's okay. UG is mg, and the high level is here at over 2. You get here. Okay, so it's up to you. Okay. Then if here, okay, the objects continue to fall down. Okay, so here you get UG mgh over 4. So here you get 3 over 4 mgh. Okay, because we have energy conservation. Okay, and finally here, you know, the high level is 0, so we have no potential energies, and we get max kinetic energies. Okay, so max kinetic energy is half mv square equal to mgs. Okay, so based on this one, you can get the Vf square. So Vf square is what? Vf square is 2gs. Right? 2gs. Okay. Yeah. Any questions? Easy, right? Yeah, and yeah, I also explain to you. We can analyze any position. Okay, any position. Okay, so any position we have kinetic energies, potential energies. Okay, next position. Okay. Any questions so far? Ben, questions? Okay. How many students haven't got IELTS 6.0? Raise your hands, please. Cũng còn hơi nhiều ha. Okay. So remember, you need to get IELTS 6.0 in semester 2. Okay. Yeah, in semester 2. Because every year's we check your IELTS certificate by 15th September. 15th September. So you need to submit IELTS 6.0 by 15th September 2026. Otherwise, you need to apply. Delay study. Okay, study. I mean, we have a gap 1 year. Okay, to try to get IELTS 6.0. Okay, yeah. Okay, so now we have these formulas of the general formulas of energy conservation. Okay, so to apply energy conservation, you need to determine the horn systems. Okay, the horn system is very important. So the horn systems, why we need a horn system? Because we need to make sure we have no external force imparting on the horn system. Okay, you can guess energies of energy conservation. Okay, so the whole system here is what? Here, the object, right? The object here, plus our system, right? Okay, yeah. So it's up to you. So if you only consider the system is the object. So we have external force, right? External force will be gravitational force. Okay, right? So again, if the systems is object, right? Plus Earth. Okay, so no external force, right? No external force. So if we define the system only objects, okay, objects only, so we have external force, right? So external force will be gravitational force, right? Right? Okay, yeah, good. So here we have the sum of kinetic and potential energies of the particles it divides in the total mechanical energy E. Okay, so E is to be constant. So E is the sum of kinetic energies and gravitational potential energies, and E is constant. Okay, yeah, yeah. Example, 3 minutes. Try to understand this example. Very easy. We have the objects, right? We have the objects is a slide down a curve frictionless surface. Okay, the body is moving 15 feet per second. When it's a 10 feet vertically above the horizontal part of the surface, that means at the beginning here, this is I, and this is final position. Final position, right? Final position. Frictionless, that means no friction force. No friction force. Okay. What else? What's in this bit V1? So V1 is VF in this case, right? Yeah. When it lies on the horizontal part of a frictionless surface. Okay. So here we can apply the energy conservation. Okay, conservation. So at the initial position, we have EI, right? AIE KI plus UGI. I mean initial position, right? And KF, EF, okay, final position. Final position we have EF, KF plus UGF, okay? So remember, we need to consider the whole system, the whole system. So the whole system contains the object, right? Surface, what else? And Earth, right? The whole systems. I mean, so the whole system is isolated system. We say isolated system. Why I say isolated system? Because no external force acting on the whole system, right? Okay. Again, if we say the system contains object, surface and the Earth, we have no external force. Okay, or we say the system is isolated. Okay. So here, initial void we have here. So at the beginning, we have Ki is what? Ki is half mvi square. And UGI, you get mghi. Okay? So at the beginning, we have the velocity 15, right? 15. Right? So now we have EI, EKI plus GUI, and we have half and we have 15 square, right? How about, yeah, we have high level, so you get G is, because here you feet, so we have 32 feet, right? So 32 feet per square second. This is the gravitational force, okay? And time 10. Time 10. Right? Do you read me? Time 10. Because G is 32 feet per square second or 9.8 meter per square second, right? Yeah. So EF is what? EF is KF plus UGF. Okay, so here you get half mvf square plus mghf. Okay, so here you know at the bottom, so he 0. This is 0, and vf we don't know. Okay, we don't know. So and we just say half mv1 square. V1 is vf because this is the whole system. This is the whole system, so we have delta EF minus AI to be 0. You know, no external force. Okay, or we can say EF is I. Okay, and then you can get final velocity. Okay, you let this one equal to this one, right? Equal to this one. You get velocity at 29 feet per second. Okay? Yeah? Yeah. So now think more. If I ask you to calculate here, okay? Here we get VF is 0, okay? So if the object continue to slide on the surface, okay, after some time with the displacement delta x, okay, this object stops. This object stops, that means VF is 0, right? I would like to ask you, what's a delta x? What's a delta x? Okay, and we assume here we have friction force. Okay, friction force, FK. Okay, FK. So now if I say mu K is 0.2, this is friction coefficient 0.2, right? Okay, and I ask you, what is the maximum distance from here, from point A to point B, such a way that the object is stopped. Okay, can you get delta x? Yeah. Yes, right? So if we know the mass of the object, right? Okay, we can get normal force. Normal force, so we can get Fk If you get FK, you can get the work done by the friction force. Okay? And then we can apply energy conservation. You can get delta X. Okay? And this is one of final exam question from previous years. Okay? Yeah. So, stop now and see you tomorrow. Do you understand what I mean? Okay, yeah, okay, good.